Lite kort om oss. Ariadna Engineering, vi är ingenjörsbyrå som jobbar med model-based definition-processer. Så vi utgår ifrån 3D-CAD-modeller, digital representation av era produkter, och vi vill nyttja det för så mycket som möjligt. Typ finita element, analys, flödesanalys, mekanismanalys, men också toleransanalys som är ett ganska stort område som vi har jobbat i många år med. Toleransanalys kräver bra specifikation av toleranser. Då predikar vi också GPS, alltså geometriska toleranser. Men MBD är ledtråden. Vi vill gärna supporta hela processen så att säga. Och det innefattar informationsspridning. Där har vi programvara från Anark, vår partner. Det kan handla om 3D-PDF, det kan handla också om webbaserad informationsspridning. Vi jobbar med automatisering av mätprocesser. Då är det CAP-Vidias produkter vi använder. Men idag som sagt pratar vi om toleransanalys, och då är det produkter från företaget som heter Sigmetrics som har följande produkter: GD&T Advisor och Wizard för formuläge. CETOL för en-dimensionell analys. Det är en fristående produkt integrerat med vissa CAD-system. Den kan läsa all typ av underlag från alla CAD-system på marknaden. Och sen det vi presenterar idag, det är fullblån 3D-toleransanalys utfört med programmet som heter CETOL, också integrerat med alla stora CAD-programvaror på marknaden. Vi kommer att använda Creo eftersom vi känner oss mest bekväma med programmet. Men det går att göra samma sak, replikera processen med NX, SolidWorks, CATIA med mera. Lite exempel på vad vi gör. Som sagt, vi jobbar nästan i 20 år nu med toleransanalys och predikar att man ska göra det. Jag har lite missionärsarbete. Exempel, här ser ni Assa Abloy lås där vi hjälpte företaget med att analysera både befintliga produkter men också nyutvecklade produkter, och där kunde vi reducera antalet prototyper, allt passade på en gång och de fick tillbaka pengarna, investering i mjukvara av våra tjänster efter 3 månader. Men om vi kommer nu till ämnet av webbinariet, det vill säga model-based baserad toleransanalys. Låt oss börja med lite begreppförklaring. Där använder vi Wikipedia. Tar vi hjälp från Wikipedia. Model-based definition innebär att hela produktdefinitionen ligger i 3D-modellen. Vi behöver inte ha ritningar. Om vi börjar däremot använda den informationen genom hela företaget men också leverantörer, kunder och så vidare, då kallas det för model-based enterprise. Och det är då man börjar få stora vinster utav användning av 3D-modeller. Vad är det som en modell kan innehålla eller innehåller? Naturligtvis noggrann geometri. Förutom geometri har vi attributer som parametrar och så vidare. Och sen har vi toleranser som idag kallas för PMI, Product Manufacturing Information. Har vi den informationen i 3D så är det ganska stor fördel faktiskt. De ska dessutom vara semantiska, det vill säga peka på rätt entitet, rätt element så att säga. Det är inte bara siffror och bokstäver. Det blir ganska stora fördelar om vi har specifikationen i 3D. Först och främst vi kan kommunicera våra krav på ett bättre sätt. Men den modellen kan användas också i många andra sammanhang. Till exempel tillverkning, automatiserad inspektion har jag nämnt tidigare, kostnadsberäkning, förlåt mig. Men idag ska vi snacka om toleransanalys. Varför ska vi göra toleransanalys? Jo, vi vill gärna balansera funktionskrav med tillverkningskostnad. Hitta rätt balans där använder vi CETOL för. När vi sätter upp en toleransanalys så måste vi tänka på ett antal element. Först och främst vilka dimensioner bidrar till variationen. Så den där lilla cylinder sitter på ett ställe. Om vi jobbar med nominell geometri, börjar vi variera dimensioner så kan det röra på sig. Sen måste vi ta hänsyn till glapp i systemet. CAD-system sällan hjälper er med detta. Så vi har externa krafter som kan flytta på komponenter eller rotera dem om ni har glapp, och det är ganska stor felkälla. Och sen så tredje elementet, det är kvalitetsdata kring era tillverkningsprocesser. Den informationen kan vi också mata in. Så det är ganska mycket information. Det kan kännas svårt att hantera det. Men som sagt, om vi tar till hjälp våran 3D-modell, så där ser ni exempel på en part som har noterat i CADen. Och då kan vi låna från modellen först och främst geometri, det vill säga alla funktionella element. De kommer in automatiskt för toleransanalys. Vi kan ta hänsyn till 3D-effekter och så vidare. Sen kan vi ta snapshot på våra assembly constraints. Så om ni matar eller kör insert, det innebär i princip att ni definierar hur komponenterna interagerar med varandra. Den informationen kan vi sno från CADen. Och naturligtvis tredje elementet, det är toleranser. Har vi dem i 3D, är de semantiska, så kan vi direkt använda dem i toleransanalys mjukvaran. Så det enda som återstår att definiera våra krav, det vi vill mäta. Och då blir det snabbare, det blir noggrant eftersom vi tar hänsyn till alla 3D-effekter. Vi kan förbättra kvalitet, reducera kostnaden och reducera antalet prototyper. Allt kommer att passa på en gång. Varför vill vi köra det här? Jo, först och främst vi vill verifiera om vi kan assemblera vår produkt. Vi vill verifiera om den fungerar, om det är en mekanism, så om den kan rotera som det är tänkt. Och vi vill ju se vad händer om vi producerar 1 miljon enheter. Hur många behöver vi skrota? Så är den här processen, kan vi upprepa den här processen med samma succé så att säga. Förstår vi varför vi har lyckats eller misslyckats? Och den här förståelse inkluderar också identifiering av kritiska dimensioner. Med digital beräkning kan vi identifiera vilka parametrar påverkar kvaliteten mest. Och sen naturligtvis bedöma kostnadsbesparingar. Vi kan reducera produktionskostnaden genom att släppa på toleranser. Vi kan välja rätt tillverkningsmetod eller rätt leverantör som levererar rätt kvalitet till lägsta pris. Det blir färre prototyper, kortare tid till marknaden. Vi kan i vissa situationer, när vi får en batch som ligger utanför specifikationen, behöver vi inte stoppa produktionen. Vi kan verifiera om det går att kompensera någon annanstans eller kanske rakt av använda den här batchen. Och generellt sett öka kvalitet, vilket innebär färre reklamationer, mindre problem med service, bättre varumärke och så vidare. Så toleransanalys påverkar mycket mer än vi tror, alltså det är inte bara siffror. Nu är det upp till bevis och då min kollega Felix kommer att ta över och visa er hur 3D-toleransanalys kan utföras i CADen.
Yes, thank you, Miroslav. Welcome everyone to this practical demonstration of CETOL Six Sigma. My name is Felix and I'm an application engineer here at Ariadne Engineering. As Miroslav already told you, we'll be using Creo Parametric for this demonstration. However, CETOL is also available for all the other major CAD systems. So why do we use CETOL Six Sigma? The great benefit is that in this case we can reuse a lot of the information we already have inbuilt in our CAD model. If I would do an Excel analysis, I would probably take a screenshot of the model, then look for all the dimensions I need for my tolerance chain, and then transcribe all that information into an Excel sheet. So that's a lot of manual work, copying all the information I already have in the CAD model. But today we're going to look at this small assembly. It's relatively small, but good to visualize the general workflow and capability of CETOL. So we have a few components here. We have something called the housing. So, or like the base of the assembly. Then we have pin here, which holds the cam component, another pin which holds the rocker component, and then a push rod through the housing up here. And we want to investigate how far this push rod sticks out from this top green surface. And that once for this current nominal cat position. But we also want to investigate how high it sticks out when I rotate the cam into its maximum position. But let's get started. On the right-hand side, you can see CETOL Six Sigma. I've connected it to my current cryoparametric application. And the first thing I want to do is add all the components I need for my tolerance chain. So that would be the housing, the pin, the cam, the other pin, the rocker, and this push rod. All right, by just clicking on the components, I've added them to my analysis model, as you can see here on the right-hand side. So if I click on one of the components, it automatically highlights within the graphical Creo user interface. So I always know what I'm looking at. And we can also see these yellow and purple symbols, which represent the assembly constraints I previously defined within the CAD model. So I can automatically add them to the analysis model. So for example, here you can see this pin is currently assembled towards the holes in the housing. Or for example, the push rod is also here in the hole of the housing, but it also contacts towards the rocker down here. So CETOL is able to read the assembly constraints from my cryoparametric model and reuse them for the assembly, for the analysis. Then in addition to that, I also get to reuse all my 3D annotations. So if you have already been using 3D tolerances, you can reuse them in your analysis model and they get automatically imported. So for example, I can again click on any tolerance within the model tree and they will get highlighted within the graphical user interface. So for example, the hole in the housing has currently position tolerance towards the datums A, B, and C. And I can see here, datum A, that's the bottom. Datum B, that's this width feature. And then datum C, that's the slot. So we get all that information automatically into the analysis model. And another great thing here is that this is a bidirectional link. So after I run my analysis and I see maybe I want to tighten this tolerance a little bit, instead of a value of 0.4, I want 0.2, this information automatically gets transferred back to your CAD model. So you don't need to go around changing those values manually afterwards. No, as you make changes to your analysis model, it will automatically get updated within the CAD model. All right, so we've added all the components necessary for the tolerance chain. We also already imported all the tolerances. And another thing, of course, if you're not using 3D annotations currently, you can also define these tolerances manually within CETOL. So if you are currently using drawings, you can just look at your drawing, add linear dimensions or geometric tolerances manually to the model. It takes a bit more work, but it's definitely possible as well. All right, so what's the next step? Well, let's look at the advisor. Here at the bottom right-hand corner, we have the so-called CETOL advisor. And that's another place where CETOL really shines. User friendliness. So Sigmatrix have put a lot of effort into making CETOL as accessible as possible. So you get all these little messages down here, which help you to create your analysis model. So for example, currently CETOL tells me that there's no measurement within my model. And that just means that I haven't yet defined my analysis objective. So let's do that. We create our analysis objective called a measure in CETOL. And I said we want to measure the distance between the two green surfaces. So I just selected two surfaces. And you can see here highlighted as the green arrow, that's now the distance I'm investigating. And here on the right-hand side, you can see the nominal distance, 10 millimeters. I can give it a requirement. So let's say I want this distance to be kept within plus minus 0.5 millimeters. And then I'll just give it a name as well. All right, so now we've defined our analysis objective. We could now run the analysis and have a look at the result, but let's look at the advisor again and what it says. So we have three messages here, and they're all the same currently. And it says fastener joint clearance is ignored. Well, what does that mean? As I click on the message, it highlights within the graphics interface again. And the message means that I have currently clearance between the pin and the hole. How can that be? In my CAD model, they are both 5 millimeters in diameter. However, CETOL also looks at the tolerances I currently have assigned to the pin and the hole. So let's look at the pin. So that one has a negative tolerance. So nominally 5 millimeters, but plus 0 and minus 0.1 millimeter. So on average, it will be a little bit smaller than 5. And if I look at the hole, that one has a positive tolerance. So that one on average is a little bit larger. So we'll have a little bit of clearance between the parts due to the tolerances. And that's what CETOL is telling us. Because currently from my CAD assembly constraint, I've set the two parts to be exactly centered towards each other. However, in reality, I have a spring force up here pushing this pin downwards, and with it all the other components as well. So if I translate that force into my pin, I should have contact at the bottom of the hole. And in CETOL, we can easily add this kind of force affecting the model to our analysis. So I'll just tell CETOL that it should engage contact at the bottom, represented to the through the little yellow ball. So with that, I've kind of gotten an analysis model much more detailed. In an Excel analysis, this little interaction can be easily missed. But CETOL will always tell us about it. The same with the other message. In this case, I have a lever effect, which would push the rocker component upwards on this side. So here, I want to engage contact on the top side of the hole. Lastly, we have the same message for the push rod and its hole within the housing. However, in this case, we are not having any force pushing it in either direction. So here I will tell CETOL to use a so-called floating constraint. And that means I want CETOL to assume every possible position of the pin in the hole and take that into account. Now that the advisor is empty, I will just run my analysis and we can have a look at the result together. All right, so this is the result screen. That's a lot to take in, but let's go through it one by one. So first of all, we have this gray and green bar, and that's the worst case result. So in a worst case scenario, the height of the push rod will differ between 8.4 and 11.4 millimeters. Then we also have this blue distribution, and in parts red here on the left-hand side, and that is the statistical result. So CETOL provides you both with the worst case and the statistical analysis. And then we have here in the middle, that's 10 millimeter, that was my target requirement, and then plus minus 0.5 millimeter, which are my limits. On the right-hand side, you can see the distribution parameters. For example, that's the normal distribution with a mean of 9.88 millimeters and a standard deviation of 0.17. And then also really useful, you have the quality metrics. And a quality metric is basically telling you how well you fulfill your current requirements. And there are a lot of kind of quality metrics you can use. It depends from company to company and industry. In this case, I'm displaying the capability, defects per million units, and the percentage of yield. Probably the easiest to understand is defects per million units. So if I would produce 1 million of these cam rocker assemblies, about 11,500 would be out of specification. And that's, of course, quite a lot. So we'll go about kind of improving the quality of this assembly. But let's look at the other information you can get out of a CETOL analysis first. So we have the so-called contribution list. And that's a list of all the tolerances in your model and how much they contribute to the overall variation. So you can see here we have 3 tolerances which contribute about 25%, and then we have a few which contribute less, down towards 0.06%. And then we have a lot of tolerances with 0%, and that just means they are not relevant for the current tolerance chain. So in our case, we have about 10 tolerances affecting the result. And in that case, of course, the worst case result is highly unlikely. So we'll be focusing on the statistical result instead. And as I click on any of the contributors, we can see what they are, either in the CETOL model tree or within the CAD interface. And again, that's really helpful for visualization. So I know this top contributor is a profile tolerance on the cam outer surface. This one is a position tolerance on this rocker surface. So the visualization can be a really good help. Apart from the contribution list, we also get to view the sensitivities. And the sensitivity is basically your critical to quality dimension, especially the top sensitivities. So for example, this one right here, again, as I click, will be highlighted in the graphics interface. So this is the height of this top surface relative to the bottom surface, datum A. That one has a sensitivity of 1, because if that one changes by 1 millimeter, it will of course affect our result by 1 millimeter. Others are not that straightforward. So for example, the position of the housing has a sensitivity of 1.5. So if I change the height of this hole by 1 millimeter, it will affect my result by 1.5 millimeter. So what does that mean? Again, I can use the visualization option to have a little animation here. So as I move the hole up and down, I will of course move the pin with it, and then I can see the effect on my result here at the top. So again, you get a lot of information to better understand the behavior of your model. All right, I said now it's time to kind of improve the quality of our product. And currently we can see that our distribution is off center. So that means we are currently not directly at the target of 10 millimeter. Instead, we have a mean of 9.88. So in this case, we want to shift the whole distribution slightly to the right to be on target. And we do that by doing a design change. In this case, we can look again on the height of the housing. That's a 1-to-1 relationship. So if I change that by 12 millimeter, 0.12 millimeter, I would move my distribution towards the target. So I could go into Creo and change that there. I can also do a little experimentation within CETOL directly. So here's the variable governing the height of the housing. Currently it's 100 millimeters long. So if I set that to 99.88, we can immediately see how that impacts our result. And we see now we're with our mean on target. And by just doing that slight side change, we have improved the quality already by quite a lot. We're down to about 3,400 defects, where we previously were at 11,500. So if you catch these things very early in the development process, you can make a few design changes to greatly improve your product. All right, so I've put my distribution on target. Now it's time to maybe tighten a few of the tolerances to get the best quality here. And in this case, I want to have a certain target in mind, and I want the target quality of CPK equals 1.33. That's a very common target in the automotive industry, for example. But of course, it always depends what kind of product you have or in what kind of industry you are. For example, in the medical, you might want a little bit higher quality. So now we can use this distribution list to tighten some of the tolerances. And in this case, I want to tighten the top contributing tolerances because that will have the largest effect on our result. So in this case, we can see here, top contributor, that was that profile tolerance on the cam, currently at 0.4. Let's see what happens if I change that one to 0.2. All right, we are at capability of 1.07, so not quite there yet. So I'll tighten a few of the other tolerances until I reach my design target. Okay, so now you can see we're kind of shooting above the goal right here. We're now at 1.48. So in this case, I can now go on the list and maybe loosen some of the tolerances to reduce manufacturing costs, because that's also a very good use of CETOL. See where I can find tolerances which don't have to be that tight while still maintaining a good quality to reduce manufacturing costs. So for example, this this profile tolerance on the tip here of the push rod is currently set pretty tight at 0.1. So if I increase that one to 0.2, that might make it cheaper to manufacture, and we still maintain a good quality. So in CETOL, you can do very quick these checks, what happens if I change my tolerance values, and you don't have to rerun the analysis every time. So you can do a lot of iteration in a very short time period. Of course, you often don't only have one specification you want to analyze, you have multiple. And I also said I want to analyze how much this distance is if I rotate the cam in the worst possible position. So I'll just import a file which shows the model in that position. So right here, we can see now we have two so-called assembly positions. One is the one we already examined, and the other one is where I've rotated the cam. So I can create this position within the CETOL model itself. I don't need to have that one within the CAD assembly. And now I have the same design objective here as well. So in this case, you can see that the height is about 23.5 millimeters. And you can see currently the quality is really bad. So here I would have to go about tightening some of the tolerances as well. So if you have a big model, that's no problem. CETOL can handle that without problems. You can have a lot of different specifications you want to analyze within the same model. You can also analyze different assembly positions if you have those. So to summarize, CETOL Six Sigma is a very powerful analysis tool which plays directly with your CAD model, so you get a lot of useful visualization options, as well as the reuse of assembly constraints and 3D annotations. Yeah, this was a very quick introduction onto CETOL Six Sigma. I will hand it now back to Miroslav, and I think we'll open the floor for some questions.
Sorry, I was muted. I just want to summarize benefits of MBD-driven tolerance analysis. You see the long list, but basically you will balance quality and cost, and it's not that difficult if you have a nice 3D model. It could be fast and pretty easy. Before we start before you open for question, I just want to inform you that we do have a lot of activities at Ariadne, for instance, model-based definition workshop at the end of September. We do basic training in GPS and tolerance analysis. You see dates there, and tolerance analysis, it's 1 day manual tolerance analysis. We are teaching, of course, we can teach you using CETOL also. We will also continue with our MBD related webcast, and 14th of October will be automation of metrology processes. So how can you automate inspection processes based on your 3D CAD model? 11th November, we'll talk about intelligent information management based on 3D model, and we will use software from Anarch to visualize it. And it will be about 3D PDF, but also web browser, how it could be used also to spread the information. And as a conclusion, if you find it interesting, please contact us for, I don't know, maybe if you want to have deeper demo of CETOL in your CAD system, or maybe you would like to run a pilot project together with us. So this was the conclusions, and now I would like to open for questions. Do we have any questions, Patrick, in chat?
Nej, jag ser, no, I don't see any questions.
Jag bytte till engelska efter Felix presentation. Alltså vi kan ta det på svenska. Så är det någon som vill ställa en fråga, så är det bara att unmuta sig själv och fråga, eller skriva frågan i chatten.
Då ska vi tillåta mikrofoner för allihopa också. Så.
I see a question in the chat, and it is it possible to use different distributions for the characteristics? And yes, that is totally possible. You can use different distributions, not just normal distribution for each of the tolerances in your model, or for each of the parts in your model as you wanted. You can also input your measurement results into the model to make it more detailed.
You want to show it, Felix? Or?
Yeah, I can share my screen. Again, let's see. So, for example, you can see each tolerance has their own distribution. And the default is a normal distribution with capability 1. However, of course, you can assign your own distribution as well. You can use a uniform distribution, for example, or you can use a so-called lambda distribution, which is a unique distribution where you can put in your mean, your standard deviation, your skewness, for example, and kurtosis. So there's a lot of options to kind of make your analysis more detail if you have that information available.
Okay, more questions? Fler frågor? Inga fler frågor, men ni är jättevälkomna att ta kontakt med oss om ni har företagsspecifika frågor eller funderingar eller vill kanske testa CETOL. Så...
Jag har en fråga.
Okej.
Typ GapGun, olika skanningsutrustningar. Har ni någon slags beredningsmodul i det här? Går det bereda sån mätning i CETOL? Har ni någon koppling till sån skanning?
Du menar optisk mätning?
Ja, precis.
Okej. Den frågan gäller egentligen CAP-videoprogramvara. Vi har stöd för detta, men det är nästa webbinarium. Vi kan diskutera det innan om du vill. Men CETOL hanterar toleransanalysberäkning alltså. Så vi kan beräkna och definiera teoretiska krav, alltså toleranser. Den verkliga variationen måste du mäta. Och då kan man göra det med olika metoder, CMM eller optiska metoder och så vidare. Det är CAP-video som stödjer kopplingen mellan 3D-modellen och dina mätdata så att säga. Där kan vi i princip lägga in hela mätinstruktioner, CMM-program om man använder CMM-maskiner. Allt kan sparas i ett format som heter QEF. Och sen kan du utföra mätningen automatiskt och så återkoppla resultatet till din CAD-modell och utvärdera där alltså. Men det är en annan mjukvara, ett annat område så att säga. Men vi pratar gärna det om du vill. Fast förutom den här sessionen så att säga.
Yep.
Bra fråga. Tack.